All right, welcome to part 2 of the calorimetry lab. In this part of the experiment, we're trying to find out what the heat of fusion of ice is. So it takes 4 joules roughly to raise 1 gram of water 1 degree Celsius. But here what we're going to do is figure out how much energy it takes to actually melt 1 gram of ice. And those phase change energies, be it fusion, which is melting, or vaporization, which is boiling, take considerably more energy to accomplish that phase change than merely changing the temperature of a material a couple of degrees. All right, so coming up with some data. We'll start again with our calorimeter. We already know its weight from above. That was the 7.5 grams. If we add roughly 60 mils of water to it, let's say we get 65.5 grams there. This experiment works best if we start a little bit warm. So typically we just take some of the water from part 1 of the experiment and get started there. So our original water was 32 degrees. We add a small chunk of ice and then just see what happens. So as we add the ice, of course, the water cools off as the ice is melting and the thermometer catches up with what's going on. We wait, say 20 seconds, but at some point we're happy with a nice stable temperature, which seems to be reflective of the solution with the melted ice in it. And then after we've got that temperature, we can leisurely go in and find out what the mass of that final mixture is. And of course, that's important so that we can calculate how much ice we actually added. All right, so there's our data. Collected incredibly quickly, and now we move on to the calculations. All right, our mass of water in the calorimeter, same as part A. We're going to take the calorimeter plus water, which we said was 65.5 grams. Our calorimeter was 7.5 grams, and so that gives us 58 grams. Coincidentally, 0.00. All right, the mass of the ice, this is taking that very last measurement we made, which was, what was that, 73.6 grams. And from that, we take away the calorimeter with the 60 mils of water in it, which is our 65.5 grams, and we get 8.1 grams of ice that melted over the course of the experiment. All right, temperature change of warm water, delta T, is again final minus initial. And so for this experiment, our final was 19.2 degrees Celsius. Our initial was the warm water, and that was our 32 degrees Celsius. And so that difference is 12.8 degrees Celsius, 12.8. And the temperature change for the melted ice. Remember for these guys that when we're talking about these experiments, the process that's going on here, if we think about a heating curve, is this is our energy going in, and this is our temperature. We're starting with ice, which is here. We're ending with water that is relatively cool. So we calculated the energy that the warm water lost, but the piece of ice is going to gain energy in 2 ways. It's going to melt, which we care about, but it's also going to raise up to that final temperature. So this one we're calculating what that little bit right there is. Or eventually we're going to calculate it. Oops, I got ahead of myself again. Anyway, temperature change for the melted ice is that we're going from 0 degrees where it melted to that final temperature. So this guy, the delta T, is again going to be T final minus T initial, but in this case the initial temperature we didn't really measure. We're just going to say it's the temperature that ice melts at. So that is TF, so that is going to be 19.2. Give myself a little space there. All right, energy lost by the warm water. Energy, once again, is mass times specific heat times delta T. And so calculating this is the mass of the water, 58 grams. Specific heat, 4.18 joules per gram degree Celsius. And a delta T for the warm water, we said was 12.8 degrees Celsius. Doing this calculation, what do I get? I get 3103 joules, and legitimately probably 3 sig figs because I recorded the temperature to the 10th place. I'll just leave that floating for now. All right, energy gained by melted ice. This is what I was referring to in the graphic up here. How much energy did it take to go from ice that had melted at 0 degrees to the final temperature? So this guy is going to be that same equation, mass times specific heat times delta T equals our mass of ice was 8.1 grams. 8.1 grams of ice will turn into 8.1 grams of water. Specific heat is that of water. Specific heat again. 4.18 joules per gram degree Celsius. And again, this is appropriate because we're talking about water here. If it was ice going from, say, -10 to -5, we'd have to use the specific heat of ice, which is different. It's about half of that value. All right, and then our temperature change was again going from 0 to the final temperature, which was our 19.2 degrees Celsius. Do the math, and we get 650 joules. All right, it's considerably smaller than the energy that was lost by the warm water, but it's still significant. And note, again, that this 3,000 joules did two things. 600 and some went to warming the water, but before the water got warmed, the ice had to melt. And so that difference, the 2,400 or whatever that is, went to melt the ice. And again, that's what we really care about. So this energy to melt ice is going to be the 3,100 joules that was available to us minus the 650 joules that got used for something else. And numerically, what do we get there? Looks like 2,450. So one last time, that 3,000 joules provided 2,400 joules to melt the ice, and then a little bit left over to warm that ice up to the common final temperature. So let's see, fill in these blanks here. Yeah, do that at the end. So our heat of fusion of ice, the heat of fusion, delta H sub F, so heat of fusion, is going to be the joules, or the energy to melt, divided by the grams of ice that were melted, and that will be the ratio then of 2,453 joules divided by 8.10 grams of ice equals 303 joules per gram. All right, if we were, oops, I got way off again. Run through this one last time. The total energy was the 3,103, took away 650, that was to melt the ice, or sorry, to warm up the melted ice. So the actual energy to melt the ice is that difference of 2,453. And again, the order of events really was that as the water was losing its 3,000 joules, the first thing that happened was we melted the ice. Once this had melted, then that residual energy went to warm the water. So we calculate it the other direction, but in order of kind of logic and what happened. First we melt, then we warm. All right, and on the bottom here, delta heat of fusion, the delta H there is heat of fusion, is going to be the energy divided by the mass. We calculated 2,453 joules to melt the ice. There was 8 grams of ice that melted. That ratio is 303 joules per gram. If we were to look this up in the literature, I believe the correct answer is about 333 joules per gram. So, again, reasonable numbers and pretty good. In this experiment, what we would expect is doing 2 trials here. We'd get the same value for heat of fusion of ice regardless of how much ice we used, because it'll come down to this ratio. If we used a lot of ice, we'd find that we needed a lot more, or that the warm water provided a lot more energy, and that would have resulted in a lower final temperature for that to work out. All right, so again, hopefully that made sense. The important thing, as always, is that we are showing our general equations. We are seeing that the units give us what we want to see, and science reigns supreme. All right, see you in part 3.